To verify the given stochastic process has the Martingale property, each random variable xt must be a ft measurable. So, we will see the definition of when the random variable xt is going to be the ft measurable. For that, the definition is as follows: let ft be a sigma field of subsets of omega. A random variable xt is a ft measurable if every set in sigma field generated by the random variable x of t is also in ft. We have a non-empty set, that is a collection of possible outcomes, and we have created the sigma field on omega, and the random variable is said to be a ft measurable. The random variable xt is said to be a ft measurable if the sigma field, if every set in sigma field generated by the random variable xt is also in f of t. If this condition is satisfied, then this random variable is going to be called as a ft measurable. Obviously, f of t is contained in sigma of x of t. So, here every element, every set in sigma field generated by the random variable xt is also in f of t. That means it is other way around. So, if that property is also satisfied, then this random variable is a ft measurable. Some remarks on xt is ft measurable. The first remark: a random variable is a random variable xt is ft measurable if and only if the information in f of t is sufficiently to determine the value of x of t. The f of t is nothing but the collection of the information up to the time t. So, whenever we say the random variable is a ft measurable, if and only if the information in ft is sufficient to determine the value of x of t. The second remark: when a random variable xt is not a ft measurable, then the information contained in sigma field f of t cannot determine the values of the random variable xt. Whenever the random variable is not a ft measurable, the conclusion is the information contained in the sigma field f of t cannot determine the values of the random variable. Whereas xt is a ft measurable if and only if it has the sufficient information to determine the value of x of t. Third remark: if xt is ft measurable and g is a Borel measurable function, then g of xt is also ft measurable. We know that x is a random variable, then and g is a Borel measurable function, then g of x is a random variable. So, here we are saying if xt is a ft measurable and g is a Borel measurable function, then g of xt is also a ft measurable. Obviously, g of xt is also a random variable. Since xt is a ft measurable, then g of xt is also ft measurable. The fourth remark: we are not giving the proof for these remarks. The fourth one: when ft is a sigma field of all subsets of omega, that is the power set of omega, and the omega is finite or countably infinite, then the random variable defined on omega is always ft measurable. Whenever the sigma field ft is the power set or the largest sigma field, in that case the random variable defined on omega is always a ft measurable. We know that whenever ft is the largest sigma field, then any real valued function is going to be a random variable. Here, whenever ft is a sigma field which is a largest sigma field or the power set of omega, and additional condition, and omega is a finite or countably infinite, then the random variable is always ft measurable. Based on xt is ft measurable, we discuss adaptability of the stochastic process. The stochastic process xt over the t greater than or equal to 0 is said to be adapted to the filtration f of t if the sigma field generated by the random variable xt, which is contained in f of t for all t greater than or equal to 0. So, this condition is nothing but xt is a ft measurable. Whenever xt is ft measurable, then the collection of random variable x of t is adapted to the filtration f of t. If this condition is not satisfied, in that case xt is not a ft measurable. If xt is not a ft measurable, then the collection of random variables x of t is not going to be adapted to the filtration. Suppose it is a xt is a ft measurable. In such cases, all events concerning the sample paths of adapted process until time t are contained in f of t. It says f of t has the information up to the time t. Whenever xt is ft measurable, then all events concerning the sample paths of the adapted process until time t are contained in f of t. It is the same meaning here. The sigma field generated by the x of t, which is contained in f of t whenever the stochastic process is adapted. In a discrete case, we say that stochastic process x suffix n can take a value 0, 1, 2 and so on, is adapted to the filtration f suffix n. So, instead of f of t, I am using f suffix n for discrete type, and similarly the random variable is also discrete type. Instead of t, I am using small n. If the sigma field generated by the random variable xn, which is contained in the sigma field fn for every n, it has to satisfy for every n, then only this collection of this collection of random variable or this stochastic process is adapted to this filtration fn. For instance, suppose Sn is the price of a stock at the end of nth day, then the price process Sn, n is equal to 0, 1 and so on, is adapted to the natural filtration Fn, n0, 1 and so on, where Fn is the history up to the end of nth day. Now, we see the definition of a conditional expectation of random variable x given sigma field f. Earlier we have defined the conditional expectation of the random variable x given other random variable y takes a value small y. To the definition as follows: let omega s p be the given probability space, let x be a integrable random variable and f be a sub sigma field of s. So, here I am defining a probability space with the omega, and this is the sigma field s, and p is the probability measure, and the random variable which is integrable, and f be the sub sigma field of s. The conditional expectation of x given f. So, to distinguish the sigma fields f and s, I am giving the s is a sigma field and f is the sub sigma field, and we are defining the conditional expectation for the random variable x given the sub sigma field of s, that is f, that is denoted by x expectation of x given f it's a unique random variable. The way I discussed, the conditional expectation is a random variable. So here the conditional expectation of x given the sigma field, that is also a random variable. It's a unique random variable satisfying the conditional expectation of x given sigma field is a measurable with respect to the sigma field f. This is a measurable. Also, the integration over any set A where A is belonging to f, the expectation of x given f, integration with respect to the probability measure p, that is same as integration with respect to the probability measure p of the integrand is simply x, integration over A. Both are one and the same. Note that the conditional expectation given the sigma field f is a random variable satisfying these two properties. And we are defining the conditional expectation given the sub sigma field of S, where this is the probability space. Notes on conditional expectation of x given the sigma field f. Note that the conditional expectation of x given f is a random variable, while expectation x is a real number. Similarly, conditional expectation of x given other random variables also a random variable, not a constant. When f is the sigma field generated by y, then we also write conditional expectation of x given f for the random variable x, expectation of x given y. Whenever f is the sigma field generated by y, you can replace f by y. Thus, expectation of x given f is the expected value of x given the information f. That means you can replace the random variable y by f whenever the f is the sigma field generated by the random variable y. That is same as the expected value of x given the information f. Whenever we say the sigma field, that is nothing but the information. We discuss the conditional expectation of the random variable given sigma field through two examples. The first example is as follows. Omega consists of 4 elements. S, that is the largest sigma field power set on omega, and the P of W's is equal to 1 by 4, where W belonging to omega. So therefore this is the set function probability measure. We are defining a real valued function. You can cross check, this is a random variable. Let f, that is a sigma field, it is a trivial one which consists of 2 elements, empty set and the whole set. Given f is a trivial sigma field, the only random variables which are measurable with respect to the trivial sigma fields are constant. The only random variables which are measurable with respect to the trivial sigma fields are constant. Hence, the expectation of x given the sigma field f, where f is a trivial one, that is same as the expectation of x, that is equal to constant. That constant you can find out by using the probability and the possible values of 0, -1 and 1, you can find out what is the constant. So here the conclusion is, whenever the sigma field is a trivial one, then the conditional expectation over the trivial sigma field, that is a constant, and that constant is same as the expectation of x, because it is no more random variable. The second example is as follows. Here the omega consists of 3 elements. S is the largest sigma field. Probability measure is defined on omega in each sample itself with the probability 1 by 3. X is the random variable. F is not a trivial one here. F is the sigma field, which is not a trivial one, and I am defining another random variable y, and that takes a value 0 or 1, and here I am claiming that expectation of x given f is same as expectation of x given y, because the y is the sigma field generated, because the f is the sigma field generated by the random variable y. If you create the sigma field generated by the y, you may land up a empty set, element A, element B and C and the whole set, and that is same as the f. Therefore, you can replace expectation of x given f by expectation of x given y. Here y is the f measurable. You can check y is a random variable also by finding the inverse images. The other properties are the first one, the conditional expectation is always greater than or equal to 0 if x is greater than or equal to 0. Then the linear property similar to the conditional expectation as I discussed earlier. Then this also I have discussed, instead of a sigma field I have discussed with the random variable. If they are independent, then both are same. The last two properties, if x1 is ft measurable, then the multiplication, the x1 taken out, which is what is known. So, since x1 is known, because x1 is a f measurable, so x1 will be coming outside x1 times the conditional expectation. If G is a sub sigma field, then this expectation, conditional expectation, is same as the conditional expectation, and this is called the tower property. I am not going to give the proof of this. Here is the reference. Thanks.